Hi, welcome to our presentation about climate change as a complex system. I'm Viktor, and this is Joakim, and this is Barbara. And this is our outline of our presentation. And I will start with talking about what climate is and what climate change is. Then Joakim will continue with showing us some models. And finally, Barbara will talk about ethical dilemmas, and finally a short conclusion. So, what is climate? If you Google climate, the first definition that comes up is the weather conditions prevailing in an area in general or over a long period of time. And when we think about weather conditions, we usually think about things like temperature, is it hot or cold, cloudy or sunny, and how much it rains. But later we also started talking about sea levels and the amount of Arctic ice. And things that really starts the climate change discussion and climate discussion is catastrophes like storms and floods. And how we measure these is usually by measure its duration and frequency and intensity. And as you can hear, there's a lot of variables like sea level, temperature, duration that we can add to the modeling of climate, which adds complexity to this problem. And as I said I was talking about Arctic ice. It's really hard to measure it all over the world, and the same with temperature, because it's different in different places. And that's because there's many different climates on Earth. So it's hard to talk about the climate of Earth as a whole, but by taking samples all over the world and with the help of weather stations and weather balloons and volunteer weather watchers and even satellites, we can get the data which we can take an average of and use when we describe the climate of the Earth. And in these measurements there's also a lot of complexity because things like tools when measuring change, and the people who measure change, and the environment where you measure change. And when I say a long period of time, I mean that the research from NASA goes back to the end of the 19th century, and and you may have heard like temperatures before that, and even back to the last ice age. And then they usually use more inaccurate measurements, like looking at the rings of trees and pollen counts and ice cores and such. And when we look at this long period of time, we see a lot of change, and that's what brings up the topic climate change. And climate change in general is the energy absorbed by Earth, the change in the energy absorbed by Earth and the energy emitted back to space. And with satellites we have seen that 30% of the sunlight, incoming sunlight reflects by clouds, and but the rest reaches the Earth's atmosphere and the Earth's surface. And as you can imagine, the Earth has to get rid of this energy in order for balance to maintain. And this is done by radiation. And forcing, or radiative forcing, is a term that is used when it comes to talking about climate change. It has the dimension watts per square meter, and it's the difference between the incoming sunlight and the outgoing radiation. And this an increase in the forcing heats the planet and an decrease cools it. So, where does this climate change come from, and what are the drivers of climate change? You may have heard a lot about carbon dioxide, the increase of the concentration of this in the atmosphere, and what it does is that it contains the emitted radiation from Earth by emitting it back to Earth, and it's one of the greenhouse gases. And water vapor is also one of the greenhouse gases, which works as an amplification for the carbon dioxide by because the carbon dioxide increases the positive forcing, which increases the temperature, which increases the water vapor released to the atmosphere, and which in turn increases the forcing. And other drivers could be things like aircraft contrails and volcanic eruptions, solar activity. And the effect of these drivers can be seen in, for example, the average temperature, which has increased by 1 degree the last 100 years. And for comparison, when back at in the end of the last ice age, when there was 3,000 feet of ice in the Northeast America, it was an average temperature which was 5 to 9 degrees lower than now. And the effects can also be seen in the melting of ice, which increases sea level, and the oceans absorbs 80% of the positive forcings applied to the Earth systems, which expands the water, increases the sea level. And other things, other effects are things like trees flowering sooner, and the catastrophes, as I talked about earlier, in storms, which has increased in duration and frequency and intensity. And when it comes to predicting the future, it's and how we affect the climate and the climate affect us, it's really hard to think about all the details and aspects which in this complex system which climate change is. So how do scientists predict that the average temperature will increase by 2.5 to 10 degrees the next coming 100 years, when, especially when a butterfly flattens wings on one side of the planet can cause a storm on the other side of the planet? To understand these effects, we have to create good models which looks at enough variables and the right variables, and that's why Joakim now is going to talk about the model.
Yeah. Okay, so the first model was developed during the late 60s, and it was developed under the belief that only a completely new approach to scientific endeavor that departed from the independent individual mode of inquiry would produce answers to complex models. So this was a model that used a lot of researchers, or a lot of researchers were involved in developing the model, and it was also the first large-scale model that was developed for a computer. And the type of the model was a general circulation model, which is what we still use today. And that is a model that simulates the general circulation of the atmosphere and the ocean and its interaction. And it's a mathematical description based on the Navier-Stokes equations. And this model was used as a learning method of learning rather than predicting, since the computing power at the time was really low. So it was really inconvenient to try to predict the future with this model, since only to simulate one model day of only the atmosphere and not accounting for the ocean or the interaction with the ocean would take 20 minutes. And when we want to predict, we want to predict longer than a few days ahead. We want to predict decades or even centuries. And that was really inconvenient at that time. But in 1975, a group of researchers used this model for some sort of prediction, where they analyzed what would happen if the carbon dioxide levels were to be doubled, and they found out that it would lead to an increase in the average temperature by about 3.5 degrees with this model. And so what has happened since then? Well, in the mid-70s, the models only simulated the atmosphere, since it was inconvenient with the computing power at the time. So this above here is what the models at the time used, and this was what scientists wanted to include in the models. So as we move towards today, we can see that there was a major development during the 90s where the computers accelerated, and it has led to a model today that considers atmosphere, land surface, ocean and sea ice, sulfate aerosol, non-sulfate aerosol, carbon cycle, dynamic vegetation, and atmospheric chemistry. So there's a lot of things going on in the model, so it's very, very complex. So how reliable are the models today? Well, one source of confidence comes from that the models are based on established physical laws. So in the case of the general circulation model, it's based on the Navier-Stokes equation of thermodynamics. One other source of confidence comes from a model's ability to simulate important aspects of the current climate. So if we were to take data outside and feed it to the model, we would and see what the model, so to speak, spits out, and were to compare that to what we see today, we could see some sort of how accurate the model is. And this is very common. So this is a simulation of the temperature anomaly where 14 different kinds of models, general circulation models, are used to simulate observed data from the 1900s to 2000. And the yellow lines are the models, where the red line is the average of all the models, and the black line is the actual observed data. So what we can see here is that there's a lot of variety within all the models. But if we were to take a look at the average of all the models and compare it to, say, the average of the observed data, we would have a really good fit. And this is really what's of interest when we try to predict the future. Since we don't really care if it's a spike here and we're a spike here, we only care about the tendency of the data. So when we try to when we want to predict, we have to add another layer of complexity, since we have to feed the model some sort of data, and this data has to be generated from a prediction of our society, how the economic growth is, or the population growth, or the technological advancements, or how our usage of fossil fuel and such. So it's a really complex system to try to predict the future with these models. And we want to look, so when we want to predict, we want to look at multiple scenarios. And these scenarios is developed from an organization called IPCC, International Panel on Climate Change. So here is the black line is just what we have seen observed data today, and from onwards here is scenarios is used. So, for example, A2 is a scenario with rapid growth, both in economic and population growth. And we can see that the global surface warming is really heading towards the doom of mankind. whereas in the orange line here is a scenario where we keep the concentrations at the level they were at 2000. So it's really complex to try to predict the future, but with an accurate model and a good scenario, it's possible. And now Barbara will talk about the more disease.
For the last 10 minutes, I will go away from all the science and the facts, and I will concentrate a little more on the philosophical and ethical aspects, which are a completely different story, but they are very important in the whole thing. And there's this guy, Richard C.J. Somerville. He's a climate scientist, and he said that we are facing three major dilemmas now, which are how to balance rights and responsibilities of the developing world. The second one, how to meet our responsibility to the future generations who must live with the climate that we are shaping today. And third, how to evaluate geoengineering schemes designed to reverse or slow down climate change. And I will now go through all the three questions and give you some ideas and approaches, but I can also tell you that I won't give you any definite answer to that, because it's really hard. The first one is how to balance rights and responsibilities to the developing world. And the first question that might arise is, who is responsible so far? And we have a really, really clear answer to that, because that is the developed world. They are the developed world because of that. Starting from the Industrial Revolution up till now, they have the highest emissions. And I mean, we're living in this luxury right now because of that. But what do we do with that? And there's something called the polluter pays principle, which means, of course, the polluter pays. In this case, it means it's the people who lived 150 years ago or 100 years ago. And the thing is, we don't even know if they did it on purpose. We don't know if they knew about the consequences. So should we blame them for that? It's hard to say, but on the other side, we could go then to something that says the beneficiary pays principle, because the polluters are dead. Who else should pay for it? That should be we as the descendants. But to argue against that is, why should we pay for what our ancestors did? It's not really reasonable, but on the other hand, of course, we're profiting and benefiting from all what they did. So again, we live in the luxury right now because of them. And in addition to that, who else should pay? Because there are some facts, and this is that the developed nations have the room for rejection, the money, and the technologies. And on the other hand, developing nations are the big losers so far, because they contributed the least and they suffer the most. They have to deal with all the consequences. They have the natural catastrophes. They have shortage of drinking water or dry periods. And they don't really have the resources to deal with that. So in the extreme cases, should we now say we deprive the right to emit from the developing world and instead allow the developing nations to catch up? I mean, that would be the fairest possibility from all. But it's really hard to do it like that, because the developed nations, they need the emission right now. They can't live with no emissions anymore, because the whole industry, the whole infrastructure is exactly made for that amount of emission. And on the other hand, it's also a little bit counterproductive to allow the developing nations to catch up now, even if that would be fair. And that leads to the next thing, that the developing nation, we say they should avoid to make more, but are we in the position to say that? Because we're living in a really good world. Everybody, or almost everybody, has a roof over his head, and should we now forbid them to come to the same level? It's really hard to answer. But with this, I will come to the next point, how to meet our responsibility to the future generations who must live with the climate that we're shaping today. And there I will just give you some ideas that are discussed now, or so, yeah. The first one is introducing an equal per capita emission without trading, which means that everybody has the right to emit the same amount. It doesn't matter where you're coming from, and it doesn't matter what happened in the past. And in addition to that, there's also something called the trading, which means that the richer countries, because they need more, because they have all the industry and infrastructure who needs it, they can buy off the poorer countries. So you can think about that, if that is good or not. It's very controversial. But what is a really good approach, I think, is distinguishing between luxury and subsistence emissions. And here I want to show you the quote from James Garvey, who really brings it to the point, I think. That is, suppose that 50% of the emissions of the US Virgin Islands are luxury and all of the emissions from Rwanda are subsistence emissions. It's clear who has room for reduction and who doesn't. Arguing the point is as good as saying some Rwandans should die so that some Virgin Islanders can recharge their phones. So it's really clear who should do something right now. But on the other hand, what is hard to say for this point, where is the border between luxury and subsistence, and who decides that? I mean, that's different for every country in the whole world. So. And another thing is that we should decide the trajectory in our ethical values. And what I mean with that is that we have benchmarks. For example, we don't want the temperature to increase more than 2 degrees, for example. But why 2? Why is it not 2.3 or 1.8? So, and the thing is, for example, what is the role of the nature and the animals in that? Maybe for us it's good to increase it for only 2 degrees, but maybe for animals it's much better if it's only 1.5. So we should really think about what we want, and we should really also consider not only us as the humans, because we are the one who are deciding now. It's not like some ice bears, for example, sitting at the Arctic and discussing about climate change. It's we. And the last thing I want to show you is the geoengineering, which is kind of creepy ways to intervene in the natural system of the Earth to counteract climate change. And as in some examples, there is solar radiation management, which wants to reflect more sunlight back to space, which can be done by space reflectors or by artificially introducing more particles that are reflective in the atmosphere. The next thing would be carbon dioxide removal, which means, of course, that you want to remove carbon dioxide. This can, for example, be done by minerals that you put in the atmosphere and they react with the carbon dioxide, and the compound is stored somewhere in the ocean, for example. Or you artificially grow plants in the ocean that absorb carbon dioxide. And these methods, they sound kind of good and they might be cheap, but nobody really knows about the effects and the side effects. And I think the biggest problem is that it doesn't really fight the roots of the problem, which is the attitude of the humans. It's only it's not solving the problem. It's maybe only shifting it a few years further. Okay, so that's what I wanted to say to the 3 parts. I hope I could make you think a little bit about it. And then I want to conclude this whole presentation. Today we learned a lot about the climate, which factors and things that influence it and that shape it. And we need the models to predict the future. That is because okay. So we need the models to handle all the factors and to put everything together to make it a little bit better. And even if we're thinking about all the ethical aspects, it's even harder to deal with all that. Okay, and so with this, I want to thank you for your attention, and thank you very much. If not, then
Okay, thank you for the presentation. And here are our questions related to a lot of those ethical points that you brought up. Number one, given that scientists in the future have knowledge of geoengineering and its effects on the climate, should it be permitted to intervene in the natural system of the Earth, for example, using SRM and CDR, carbon dioxide reduction and
Solar radiation.
And if so, what restrictions for this would be appropriate? And to go along with this, there was also a quote by the Richard Somerville guy. I feel about geoengineering exactly as I do about nuclear war. Study it by all means, but never try it.
Right, the second one. Should developing countries be granted greater allowed emission quota than developed countries, since the current developed countries, as you said before, historically stand for the vast majority of pollution? What other solutions could there be regarding this issue? Discuss advantages and disadvantages for the different methods that were mentioned.
And number three, assuming equal parts per capita, should it be allowed to trade emission quota? What would this incentivize? And would it be easily exploitable by richer nations, or would the world market self-adjust to compensate for this approach?
Right, and lastly, basically what qualifies a luxury and subsistence emission, right? Some examples how to divide them, basically.
Thank you.
Okay. So, well, yeah, thanks